Hello everyone, welcome to EN4593 Autonomous Systems module. In this lecture we are going to cover the third and the final part of Gaussian filters. Here is the outline for this lecture. First we will have a recap on what we studied last time. In this lecture we are going to discuss nonlinear systems and how we will linearize them to continue using linear system theory. Next, we will study about how we can use linearization techniques to transform Kalman filter into something called the extended Kalman filter to tackle with nonlinear systems. Finally, we will look at sensor fusion using Kalman filter. In the previous lecture, we identified Kalman filter as the optimal state estimator for linear Gaussian systems. So if we are to employ the Kalman filter to our application, we should make sure we have linear Gaussian state transition, linear Gaussian measurement model, and Gaussian initial belief. We saw that some terms of the Kalman filter could be computed offline, and it is helpful especially for embedded systems. We looked at a target tracking example to understand how we can use Kalman filter in an application. Finally, we realized that we may experience issues in convergence and performance when Kalman filter is used in real applications. Okay, in this lecture, we will be mainly looking at nonlinear systems. Up to this point, we were looking at linear systems. Unfortunately, linear systems do not exist in real life. All systems are ultimately nonlinear. Even one of the most simple relationships we know, the Ohm's law, that is V equals IR for a resistor, is only an approximation over a limited range of operation. As you can see in this figure, if the voltage exceeds a certain threshold, then the linear approximation will break down. So does that mean all what we have learned so far regarding linear systems is of no use? Well, even though not as mature and cohesive as linear techniques, nonlinear state estimation techniques are becoming widespread now. We can observe two main approaches to deal with nonlinear systems. First one is the linearization. In that, we basically assume the nonlinear system with a linear approximation and limit ourselves to a certain range where the approximation holds. An example would be the extended Kalman filter, which is undoubtedly the most widely used nonlinear state estimator. The second approach is called Monte Carlo approach, where the problem is addressed using numerical simulations. Particle filter is a very good example for Monte Carlo estimator, which we will discuss later. So there is still a lot of room for advances and improvement in nonlinear estimation techniques. Now, if we consider state transitions and measurement models, they are rarely linear in practical applications. That is, we would have nonlinear functions in the form xt equals some function g utx t minus 1 plus epsilon t, which is zero mean Gaussian noise. And for the measurement model, we would have zt equals h xt plus delta t, again zero mean Gaussian noise. Okay. Now let me show you an example. Let's say we have a mobile robot and it is given with a translational velocity v. So let me draw the coordinate axes like this, x and y, and we have our robot and it is being given with the translational velocity v. So this is simple x and this is simple y, and the heading direction, let's say, that is theta. Okay. Now if I ask you to write the discrete time state transition model. Can you do that? Assuming you have finished, we can write the discrete state transition as xt. So this is the x component is equal to its previous location plus, now the velocity in x direction is v cos theta t minus 1, okay, times the time step dt, right? Then we have the noise component in x direction. So here this is our control input. Similarly, in y direction we would have yt minus 1 plus v sine theta t minus 1 dt plus the noise. So with this translational velocity v, ideally we should not expect any change in the heading direction. So this should be equal to its previous heading direction, but we know that there is a noise component, right? So with noise it can change. So this is the state, okay? Now we see that the state transition model contains cos and sine terms. So these are nonlinear functions, so we are unable to apply the standard Kalman filter in this case, right? So let me write that. We can't apply Kalman filter. Okay. We can understand the impact of a nonlinear transformation of a Gaussian in this figure. So when we input a random variable with a Gaussian distribution, so this is our input, and here we have a nonlinear function. Okay, so you are going to get some strange looking PDF which we may not even be able to compute in closed form. So here we have the output. So this is what we would get, but we are unable to get a closed form solution. So what we have done here is use many samples as possible to get this shape, right? So I may write it as cannot be computed in closed form, right? But we can do something interesting. That is, if we can find the mean and the covariance of the original distribution, then we can have a Gaussian distribution with the same parameters. That is the same mean and same covariance. So that's what we have here in this dark line Gaussian distribution. Okay, so this is like an approximated Gaussian based on mu and sigma. Actually, that is going to be the idea for our next topic. Alright, now we are going to look at the topic of linearization. Linearization is the assumption of a nonlinear system with a linear system approximation. In linearization, we need to make sure that we do not move away too much from a certain linearization point to keep the assumption valid. Okay? So how do we linearize a nonlinear system? We are going to use the Taylor series expansion of a function to achieve that. Alright, do you remember the Taylor series? Shall we write it here? So we can write the Taylor series as fx equals fa plus x minus a times the first derivative of the function at a over 1 factorial plus x minus a to the power of 2 and the second derivative of the function at a over 2 factorial and so on. I hope you got it right. So what is this a? When we write the Taylor series, we are writing our function fx about a certain point a, right? We call this as the operating point. Then what is first order Taylor expansion? Now if we assume our x is very close to the point a, then the higher order terms, for example this one, these would be very small, right? And we can neglect them. Then we would be left with only the first two terms. Therefore I can write the first order Taylor expansion as fx equals fa plus x minus a times f dash a, right? We have neglected the higher order x minus a terms, right? I can rearrange these terms to write f dash a times x plus f a minus a times f dash a. Okay. Now we have a linear form. So this has the form of y equals ax plus b. Basically what we have here is we have assumed fx to be a linear function about the point a, and a is known as the linearization point or the operating point, right? So visually, let's say this is fx and this is x. So we have chosen a certain point a, right? So I have the nonlinear function, but we have linearized it. So this is the linearized function. And this is linearization point. Okay, so as long as x is near a, our linear approximation is valid. Or in other words, we should make sure x is not too far away from a. Okay, so this linear approximation or this linear function seems okay within a certain range, that is near to a. If we go too far away from a, we can see our approximation deviates from whatever the nonlinear function we have. Understood? Alright, now we are going to linearize the state transition model using the first order Taylor expansion. Our first question should be, linearize about where? What should be our linearization or operating point? Now it is very important to choose the linearization point carefully, because if we are too much away from the actual state, then our approximated linear system is going to be different from the nonlinear system we have at our hand. So what should be the best estimate for xt minus 1 that we should choose to linearize the function g? Any thoughts? Well, we can choose mu t minus 1 because that is the current best estimate we have about xt minus 1, right? So we can choose this guy, mu t minus 1, and that is where we are going to linearize the function g. So this is our current best estimate. Okay. So using the first order Taylor expansion, shall we linearize the state transition model at mu t minus 1? Well, we assume ut is known, so we take it as it is. Okay, so we can write this as g ut, and this is the linearizing point mu t minus 1 plus the first derivative at ut and mu t minus 1 times xt minus 1 minus mu t minus 1. Okay, so this guy is known. So the first derivative, that is this one, g dash mu t ut, this is equal to the partial derivative da bar over da bar x t minus 1 for g xt minus 1 ut evaluated at mu t minus 1. Okay, and we call this as gt, which is the Jacobian of the function. So ultimately, using the first order Taylor expansion, the state transition model is linearized to be g ut x t minus 1, so that is approximately equal to the Jacobian gt times x t minus 1 plus the remaining terms, right? G ut mu t minus 1 minus gt mu t minus 1. Okay, so the operating point or the linearizing point was mu t minus 1, which was the current best estimate. Understood? Let's do the same example to fully understand the linearization of state transition. So here we have the mobile robot given with a translational velocity v, and we already obtained the equations for state transition. Okay, now one thing to note is that xt minus 1 is a vector, and therefore g will be a function vector. That is, we can write g as ut x t minus 1. So we have three components. x t minus 1 plus v cos theta t minus 1 dt. Next we have y t minus 1 plus v sine theta t minus 1 dt, and finally we have theta t minus 1. So the deterministic parts come here into the function g, and this is a 3 by 1 vector. Okay. Next we need to find the Jacobian. Here we are dealing with a function vector and a state vector having same dimensions. So the Jacobian would become an n by n matrix. So in matrix calculus, we usually follow certain conventions, and once a convention is followed, we have to stick to that. That's all, okay? So let's take the function vector as g1, g2, and g3. And for the Jacobian, gt, we first take g1 and take partial derivative of that with respect to all the elements of x. And in the convention we will stack them in the first row. Okay, so we have dabba over dabba x t minus 1, that is the first element of the state vector. So it's for g1. Again we take g1 and then take partial derivative with respect to the second element, y t minus 1. Similarly, we have theta t minus 1 g1. Okay, so that's our first row. Next we take g2 and again take partial derivative of that with respect to all the elements of x. So we have dabba over dabba x t minus 1 for g2, again g2, and dabba over dabba theta t minus 1 g2. Okay, finally we do the same thing for g3. So we have g3 and g3. So what would be our resulting Jacobian matrix? Shall we calculate that? By the way, this is a 3 by 3 matrix in this case. Okay. So what's left to do is calculate these individual entries. So if we take the first one, we take g1, that is this expression, and we take the partial derivative of this guy with respect to xt minus 1. So what's the answer? That is 1. Okay. Again we take g1 and take the partial derivative with respect to yt minus 1, and there is no y here, so that is going to be 0. Okay. And how about we take the partial derivative of g1 with respect to theta t minus 1? What do we get? So we will get minus p dt sine theta t minus 1. Agree? So we can fill up the remaining entries. So here again we have 0 and 1, and here we have v dt cos theta t minus 1. Okay, and finally g3, so we get 0, 0, and here we have a 1. Now this should be evaluated, this Jacobian gt should be evaluated at mu t minus 1. So what does that mean? So it means for this theta we should take mu t minus 1, and from that state vector we take the third element and put that here, right? And we do the same for this one. And we already know the control input we gave, V, and we also know what dt is. So we can populate the Jacobian matrix for mu t minus 1. Understood? Alright, next we are going to linearize the measurement model using the first order Taylor expansion. Again, our first question should be linearize about where? Or what should be our linearization or operating point? What do you think? Is it the same mu t minus 1 that we used before? Or do we have a better linearization point when it comes to measurement model? Any ideas? Now, if we look at the Kalman filter, when we are about to use the measurement model, we have completed the prediction step using the state transition. So at that moment, our best estimate about the state would be mu t bar, right? Do you agree with that? Previously it was mu t minus 1, but since we have incorporated the control input, now we have a better estimate than mu t minus 1, which is mu t bar, this guy. Right? So we are going to linearize h about mu t bar. With that, shall we linearize the measurement model? Using first order Taylor expansion, we can write h xt approximately equal to h mu t bar plus h dash evaluated at mu t bar times xt minus mu t bar. Okay. Again, this guy h dash evaluated at mu t bar is equal to da bar over da bar xt h xt at mu t bar. So this is again the Jacobian ht. Ultimately, we can write h xt is approximately equal to ht xt plus the remaining terms. Understood? Let's do a simple example to fully understand the linearization of measurement model. Let's say we have a range bearing sensor that is something like a sonar, IR or LiDAR sensor to detect an object. Okay, so again let me start with the coordinate frame x and y, and here we have our target and this is our sensor. So we can get the range and the bearing to the target. So this would be simple x and this is simple y. Okay, so the measurement we get from the sensor would be a range and a bearing. So the measurement RT, in terms of state we can write the relationships. So RT would be equal to square root of xt squared plus yt squared plus some noise component, then the bearing phi t equals tan inverse yt over xt plus the noise. Okay, so here our state we have assumed that to be xt and yt for this example. Alright, again we have a function vector h with two components, so we can write h xt equals the deterministic parts and second one would be tan inverse yt over xt, right? This is 2 by 1. Okay, next we need to find the Jacobian. Again we have a function vector h and a state vector, so the Jacobian would become an n by m matrix where n is the state dimension and m is the measurement dimension. And let's take the function vector as h1 and h2. Okay, so for the Jacobian ht, we first take h1 and take the partial derivative with respect to all the elements of state vector x. Let's write that here. So we first take xt and h1, and then we take with respect to yt h1. Similarly, we take h2 and again take partial derivative of that with respect to all the elements of x. So here we have h2 and h2. So this would be a 2 by 2 matrix. Okay, so what would be our resulting Jacobian matrix? Shall we calculate that now? So if you did that right, for the first entry we take h1, which is the square root thing, and get the partial derivative of that with respect to xt, right? So your answer would be xt over square root of xt squared plus yt squared. And we will get a similar expression for the next element. So we have yt over square root of xt squared plus yt squared. Okay, so what about the second row? So we take h2, which is tan inverse yt over xt, and when we get the partial derivative we get minus yt over xt squared plus yt squared, and here we get xt over xt squared plus yt squared. Okay, so this Jacobian matrix ht should be evaluated at mu t bar. Okay, which means we take the mean vector mu t bar and substitute for x and y values. Understood? With those supporting materials, now we are ready to have a look at the extended Kalman filter. So my plan is to derive the extended Kalman filter equations by looking at the standard Kalman filter. So we had linear models for the Kalman filter, and now we have linearized models from nonlinear equations to extend the Kalman filter for nonlinear systems. When we do a quick comparison between the two sets of equations, we see that AT and GT have correspondence with each other, right? And also we see that CT and HT have correspondence too. So GT and HT are Jacobian matrices. Okay, so let me write that here, AT and GT, and then we have CT and HT. Okay, to obtain the expressions for EKF, let's go line by line. So in the second line of the standard Kalman filter, we have the predicted mean, right? Mu t bar. So that is obtained by setting xt minus 1 to mu t minus 1 in the deterministic part of this equation, right? So I can do the same thing for the linearized version as well. I take the deterministic part, this one, and I can send xt minus 1 to mu t minus 1. Shall we do that now? So mu t bar would be equal to gt xt minus 1 plus gut mu t minus 1 minus gt mu t minus 1. So here xt minus 1 is to be replaced by mu t minus 1. Okay, so when we do that, what do we get? So this one and this one would get cancelled off, and the result would be g ut mu t minus 1. Okay, now transforming the third line of the Kalman filter is pretty straightforward. Just replace AT by GT. Okay, shall we write it here? So sigma t bar is equal to GT sigma t minus 1 GT transpose plus the process noise covariance matrix, which is R3. Okay. Similarly, we can transform the fourth line for the Kalman gain, where we can replace CT with HT. Okay, so we can write that equation as well. So we have KT equal to sigma t bar HT transpose. So we are substituting for CT. Then we have HT sigma t bar HT transpose plus the measurement noise covariance QT and inverse. Right. Now for the fifth line here, mu t, we need a predicted measurement. So here we have a predicted measurement, right? So how do we get that? So in the standard Kalman filter, if you look at the measurement equation, we can get that predicted measurement by taking this deterministic part and substitute xt with mu t bar, right? So similarly, we can do the same thing for the measurement equation for the linearized version, right? So we take this expression and replace xt with mu t bar. Shall we write it now? So we have mu t equal to mu t bar plus the Kalman gain KT times the measurement is at T minus, so we will write the predicted measurement from the linearized version. So we have HT xt plus H mu T bar minus HT mu T bar. So that should be evaluated at mu T bar, or we replace xt with mu T bar. So when we do that, what happens is this and that gets cancelled off. So our answer would be mu T bar plus KT times ZT minus H mu T bar. Understood? Okay, finally, for sigma T, we will use HT, the Jacobian matrix, instead of this CT, right? So we'll write sigma T equals I minus KT HT times sigma T bar. That's it. Okay, so here we have the equations for the extended Kalman filter. Now let me emphasize that this is not the proper way to derive the extended Kalman filter, but this is like a shortcut instead. So please remember that, and let me write it also. So that this is not the proper way to derive EKF, but I looked at the standard Kalman filter equations and did a transformation using the linearized modulus. Okay. So here we have the algorithm for the extended Kalman filter. Similar to the standard Kalman filter, it will take in the previous mean and the covariance, the control input and the measurement, and output the estimated mean and the covariance. So this is also a parametric filter where we have two parameters. Okay. And GT and HT are Jacobians. So let me write that here. GT, HT, Jacobian matrices. And KT is the near optimal Kalman gain. Okay. Now the extended Kalman filter is a suboptimal estimation technique, and it is obvious because we use the first order Taylor expansion by leaving out the higher order terms, right? Therefore it cannot be an optimal estimate. Understood? Can we do any offline calculations in extended Kalman filter similar to the standard Kalman filter? Well, you already saw that the Jacobian GT depends on mu t minus 1 and the Jacobian HT depends on mu t bar, right? So that means, unfortunately, we cannot perform any offline calculations in EKF. So everything should be done in real time. Alright, now let's move on to discuss some practical considerations regarding extended Kalman filter. Simplicity and computational efficiency are the two main strengths of EKF. So EKF is very simple to implement, just like the Kalman filter, and it is also computationally very efficient. So unlike Monte Carlo techniques, which we will discuss later, EKF does not need high-end computers for implementation. So what are the limitations of extended Kalman filter? Can you think of any? Now, since we use linearization to formulate the EKF, there can be several associated problems. So one problem is the nature of the input random variable at each iteration. That is, if the variance of the random variable is too high, you can see in this figure what happens to the distribution of the resulting random variable. So here we have high variance, right? So you can see at the output it is far from being Gaussian, right? So the resulting PDF does not look Gaussian at all. But if you look at the figure on the left, here you can see, you will appreciate that when the variance is low, so let me write that here, low variance at the input. So there is no problem approximating the resulting distribution as a Gaussian, right? So in other words, when the samples of the random variable are distributed far away from the operating point, the linear approximation will be no longer valid, right? So we need our samples to be very close to the operating point. Another problem regarding the linearization is the actual linearization point. So if we input the same Gaussian at two different operating points, you can observe in this figure what happens to the resulting distribution. So in the right-hand figure, you can see that the function is almost linear within the most significant portion of the Gaussian. Therefore, the resulting distribution would also be a nice Gaussian. However, in the figure on your left, it is not the case. In that, we see that even a slight change from the operating point can deviate from the linear function, and therefore the resulting distribution will no longer be a Gaussian. Okay, so we can learn two things from this. Number one, we have to accurately model the state transition and measurements as much as possible to benefit from the strengths of the EKF. Number two, if the problem is highly nonlinear, we should seek other nonlinear estimators such as particle filters instead of extended Kalman filters. So let me write the problem here, which is different linearization points. Okay. All right. The last topic of Gaussian filters is sensor fusion. In the Kalman filter algorithm, we already saw that it fuses two information together, considering their uncertainties. The information regarding the control input and the information regarding the measurements. In fact, we can actually fuse more than one measurements in the correction step. And that's how we achieve sensor fusion using Kalman filter. There are two main ways to fuse measurements from multiple sensors. The first approach is to have a single measurement model that takes into account all the measurements. And the second approach is to iterate over the correction step for each sensor input. So in the coming slides, we will have a look at them in more details. We can understand the two approaches better if we take an example. So let's take the same target tracking example and let's assume there are two sensors providing measurements. Okay. Suppose sensor 1 tells us both X and Y locations of the target. So sensor 1 gives us both locations, and here we have our state. Then we have noise components. So the C matrix would be this one. Okay, so I will call it as C1, right? Next, we will assume that sensor 2 only provides us with X location of the target. So sensor 2 gives Z xt, and we have the same state here and the noise. So in this case, the C matrix would be just 1 0 0 0. Let me call it as CT2. Okay. So what I'm going to do is I will merge the two C matrices together to create a single C matrix. So I have my measurement vector zxt, zyt, and let's call the third one as z-xt. And I have the state xt, yt, xt dot and yt dot. So I'm taking ct1 and ct2 and merge them to create the new C matrix. And I will call it as CT dash. Okay, and of course I have the noise components as well. That is, I will create the corresponding noise covariance matrix. So this is Gaussian 0 mean, and let's call it as QT dash. Okay, so you should remember that I have silently assumed that both the sensors are in synchronization, or otherwise I can't do this. Okay, so with this new measurement model, sensor fusion will be handled automatically in the Kalman filter. The second approach will update or correct the estimate one after the other. So in other words, we will first take the measurement from sensor 1, go through the Kalman correction step and obtain mu and sigma, and go back to line 4 and repeat the same steps one more time for sensor 2. Okay, so in the second time we will be using the corrected mu and sigma by sensor 1 instead of mu t bar and sigma t bar. Okay, so we are going to iterate, that is, we can have a loop for each sensor we got. So here we have some loop for each sensor. And once all the sensors are visited, we can output the resulting parameters mu and sigma. again, I have silently assumed that the sensor readings are in synchronization. So this is the second approach for sensor fusion. Okay. Now I actually want you to check the results from both the approaches, and let's do that as a homework. Okay. The assumption of synchronized sensors is not reasonable most of the time. So how do we tackle the problem of synchronization? Here I will tell you a basic implementation we use to deal with out-of-sync sensors. So when we implement a state estimation filter, one way to do it is like this. Let's say we have a timer that gets triggered at a frequency we want to run the Kalman filter. For example, suppose our Kalman filter gets triggered at 10 Hz. Okay, so in these figures, the time instances marked in black, these ones, tk minus 2, tk minus 1, and tk are those instances where the Kalman filter gets triggered. Okay, now there will be separate threads running for sensor measurement callbacks. That is, for example, say we have a camera sensor that gives measurements at 30 Hz. And furthermore, we might also have an IMU sensor that gives measurements at 50 Hz. So they will have parallel threads to update the incoming measurements. So in this figure, we can have camera measurements in purple color, for instance, and IMU readings in green color. Okay. Now the reason why the frequency of Kalman filter is low is because we want to give it more time to do all the matrix calculations regarding prediction and update steps. So with this setting, suppose we want to update the Kalman filter for the time step tk. But we do not have measurements for tk here, right? So what we do is take the latest measurements for both the sensors and choose the timestamp to the one that occurred first. So out of these two, we will choose the timestamp as the purple one. Okay, so I have set filter update stamp to this one. Now we are going to do the prediction step up to this new timestamp instead of tk. So in an ideal setting, we will predict from here to there and get it corrected from measurements, and predict from here to there and get it corrected from measurements. But since we don't have measurements for tk, we chose this one as our timestamp. Therefore, we are going to predict from this timestamp to only up to this one. So we will adjust delta t to this purple timestamp. Okay. And the next thing we are going to do is we are going to interpolate the other sensor reading, which is in green color, to this new timestamp. Okay. So now we have synchronized sensor readings because we have one purple one is at that timestamp, and we did an interpolation for the green one to that timestamp, and also we predicted only up to this timestamp. So everything is available for this timestamp, right? Now the reason why we do not choose the timestamp of green sensor, I mean this one, is because we do not normally do extrapolation. So it is something in future for the purple one, right? For this guy, this timestamp would be something in future, which we do not know. But when we interpolate, we are predicting something in between that had already happened. So that should be reasonable. Understood? With that, we have come to the end of this lecture, and that will also conclude our discussion on Gaussian filters. Let me summarize what we discussed in this lecture. So in real-world applications, we mostly encounter nonlinear models. Therefore, the usage of standard Kalman filter is limited. Using the first-order Taylor expansion, we managed to linearize nonlinear state transition model as well as nonlinear measurement model. And we did that about an operating point, and we could formulate the extended Kalman filter for nonlinear systems. We understood that EKF is a suboptimal state estimator for nonlinear Gaussian systems. And finally, we saw how we can use Kalman filter for the purpose of sensor fusion. Thank you.